Next, let's look at Chapter 6, CPU scheduling. In this chapter, we are going to talk about 4 things. The first thing, we will talk about the basic concepts of a CPU scheduling, and then we will talk about the scheduling criteria, basically how we use the scheduling criteria to compare and evaluate different scheduling algorithms. Then we will introduce numbers of scheduling algorithms. At last, we will briefly talk about thread scheduling. Remember, we have talked about how to load a program into the system, then becomes a process. Then the process has been executed in the system until it is finished. So normally, there will be a switch as a cycle. So the process will do some computation as a CPU burst, then do some I/O as I/O burst, and then the process will go back to the CPU to execute some other instructions, then followed with some other I/O. So continually keep this cycle until the process is terminated. So when the process is doing the I/O, the process will wait for the I/O device to finish the operations. However, the CPU is idle there, right? So do you remember when we talk about the multi-programming in Chapter 1? So in order to maximize the CPU utilization, the main idea is so when one process is doing the I/O, we will do the scheduling. So we will record the status of the current process and move the current process out of the CPU. Then move another process onto the CPU to keep the CPU as busy as possible. Another thing I would like to mention is that so during the lifetime of a process, the running time of each CPU burst may not be the same, so which makes the CPU scheduling even more complicated. In Chapter 3, I have mentioned that CPU scheduler is also called short-term scheduler, so which selects processes from ready queue and assigns CPU to one of them. So based on different scheduling algorithm, the queue may be ordered in different ways. So we will talk about the details of that in later slides. The scheduling decision may take place on different situations. So for example, process switches from a running to waiting state, running to ready state, and waiting to ready, or process terminates. For the first and the fourth cases are referred as a non-preemptive. So for example, when the process finishes computation and start to do the I/O, then the CPU can be scheduled to other process. Or when the process is terminated, the CPU can also be scheduled to other process. On the other hand, for the other two situations belongs to preemptive. So for example, one process is not finished the computation. However, due to some reason, the current process has to be suspended and taken off of the CPU and put onto the ready queue, so whenever the CPU is available, the suspended process can be put onto the CPU immediately. The other situation is that so when the process has been finished the I/O, it should be put onto the CPU immediately, right? However, since other process is running on the CPU now, so it will be put onto the ready queue and ready to be executed whenever the CPU is available. The other important component is called dispatcher. The dispatcher module gives control of the CPU to process, and the process is selected by short-term scheduler or CPU scheduler. In order to achieve that, actually there are 3 steps that the dispatcher needs to do. The first step is to do the context switch, which switch the process that is selected by the CPU scheduler onto the CPU. After that, Since previously the hardware is controlled by operating system, which is in the kernel mode, so now we need to return the control of the CPU to the selected process, which means we need to switch from kernel mode back to the user mode. And then the next step is to resume the next selected process to be running on the CPU, so which is referred as jump to proper location in user program to restart that program running. During this whole procedure, there is another term called dispatch latency. The formal definition of this term is that time it takes for dispatcher to stop one process and start another process to run. Then let's look at the scheduling criteria, which is used to evaluate the performance of a scheduling algorithm. Here list 5 common scheduling criteria. The first one is the CPU utilization. So since we want to keep the CPU as busy as possible, that is why we need to do CPU scheduling. In a CPU scheduling algorithm, so we may want to maximize the CPU utilization. The next one is throughput, so which is the number of processes can be finished within 1 unit of time. Again, given a scheduling algorithm, we want to maximize the throughput. So which means we want to maximize the number of processes that can be complete within 1 unit of time. The third one is turnaround time, which is defined as the time that when we start a process, we start a timer at the same time. When the process is terminated, then we stop the timer as well. The time recorded by the timer is called turnaround time. So of course, when you start a process, you want the process can be finished as soon as possible, right? So therefore, in a CPU scheduling algorithm, you may want to minimize the turnaround time. The fourth one is waiting time, which is defined as amount of time that the process is waiting in the ready queue. So later you will know you may do the calculation by using a turnaround time taken by the CPU execution time for this process. So surely, in order to make the process can be terminated as soon as possible, so we may want to minimize the waiting time in the scheduling algorithm. The last criteria is the response time, so which is evaluated from a user's perspective. So therefore, the response time can be calculated from the beginning of a process to the first response, which can be realized by the user. So the response can be a data output, or screen update. So of course, we want to minimize the response time for the scheduling algorithm to improve the user experience. And also, when we evaluate the performance of a scheduling algorithm, so we are really care about the performance of a single process. So instead, we are more care about the overall performance for all the processes. So therefore, we may consider average, minimum, or maximum of those criteria. For example, we may want to minimize the maximum waiting time among all the processes.